Swayam Prabha. Digital India. Educated India.
Hello everyone, today I am going to deliver a lecture on welded joint static analysis. Here I will discuss about welded joint subjected to bending moment. So, last class I have already discussed about the theoretical background of welded joint which is subjected to bending moment. Then what should be the design dimension of that welded joint. That theoretical background I have already discussed in previous lecture. Today I will solve some problem on these topics. So, here this is the content of today's lecture, that means here I will solve some problem related to welded joint subjected to bending moment. So, last lecture I have already discussed that to solve the problem related to welded joint subjected to bending moment, there we generally follow 4-5 different steps. What are those steps? Little bit I am explaining here, after that I will directly go to. So, the first step of finding out the design dimension of welded joint subjected to bending moment, the first step was to find out primary shear stress, So, this primary shear stress which we generally represented as tau 1. So, this tau 1 equal to we know that force P divided by total cross section area of all weld. The second step was to find out, that means find the bending stress, because here this welded structure or welded joint is subjected to some bending moment. That is why due to bending moment, whatever the stress developed in that welded joint, that is called bending stress. This bending stress is a type of normal stress, that means which is acting perpendicular to the throat cross sectional area, that which I have explained in previous lecture itself. So, second step is to find out the bending stress. Actually you can say the maximum bending stress sigma b, which is equal to your m y by I. Here we generally consider for finding out the bending stress second moment of area, or you can say moment of inertia, which is along its axial direction of that, if it is a beam. So, along generally axial direction we consider x axis, that is why we can say that should be the Ix, that means moment of inertia about x axis, and here this y should be the distance between this x axis to the farthest weld axis, that means this is the perpendicular distance between these two axes. That means one axis is passing through the weld itself, that means farthest weld itself, another axis is passing through the its CG of weld and along the beam axis, that you can say. So, this is the farthest distance you can say. So, this distance y is the y axial distance, okay. That means perpendicular distance between that weld axis and axis of that beam, if it is a beam. Now, third step is to find out the maximum shear stress. So, last lecture itself I have discussed about how to find out the maximum shear stress. So, there we have observed that maximum shear stress tau max, or you can say tau resultant, due to this primary shear stress and bending stress is equal to sigma b by 2 whole square plus tau 1 square, because here the state of stress of a element of the weld you can say is tau 1. We know this element should be balanced, that is why what happens in this element, if there is acting a tau 1 in upward direction, then to balance this, it is a self balanced types of stress. So, in top side and bottom side there will develop a clockwise types of moment. If there is a upward and downward, if there is a anti-clockwise types of moment due to this primary shear stress, then top and bottom side generally there should be clockwise types of effect on this primary shear stress. So, here the state of stress of a element due to this combined stress, that is sigma 1 and sigma b, is like this, you can say. So, for this case, if the state of stress of a element of the weld is like this, then we know this maximum, or you can say resultant shear stress or maximum shear stress of that element will be square root of sigma b by 2 whole square plus tau 1 square. This is already I explained in previous lecture. And the fourth step is to find out the design weld dimension. How we find out this thing? This we find out based on the permissible shear stress of that weld. So, that means if the permissible shear stress of that weld is tau p, then this we should compare with the resultant, or you can say maximum shear stress. From here generally if we just compare these things, we can easily find out what is the throat thickness T, and if we know this throat thickness T, then we can easily find out what is the leg length H. So, leg length H is generally T by 0.707. So, by this generally we can easily find out the design dimension. So, these are the main steps we have to follow to find out the design dimension of the weld once it is subjected to bending moment. So, first of all, by using this following step, we will solve one problem. The problem statement is like a bracket is welded to the vertical column. So, you see this is a vertical column, here a bracket is welded by means of two fillet weld as shown in this figure. Two fillet weld means this is one fillet weld, this is another fillet weld. So, once we see it from front side, then we can see this front view is shown in this left side, you can see. So, this is one weld and this is another weld. So, by this two weld generally this bracket is connected with this vertical column. So, here we have to determine the size of the weld. So, here what are the things required to do? Here we have to find the size of the weld. So, what do we mean by size of the weld? Size of the weld means we have to find out T and H. T is throat thickness and H is called leg length. This we have to find out. What is this T and H? Here the permissible shear stress in the weld is given as, so here tau permissible is given as 70 MPa. So, this is given, and another thing given is here the load P is given. So, load P is 10 kilonewton is given. These are the things is given data. So, by using this given data and dimension of this bracket, we have to find out what is the throat thickness T and leg length H. So, we will now start solving this problem. So, first step is to find out the primary shear stress. Primary shear stress. Because once we solve one problem, then you will get the idea how to solve the problem of this kind. Okay. So, primary shear stress tau 1, this we know as this load P divided by total cross section area of all weld. So, here area of weld is how much? Here let us consider. So, here let us consider the throat thickness of the weld equal to T. So, here length of the weld is given as 50. So, we know here 2 welders of similar kind are there. So, 2 into total cross sectional area of wall weld at throat thickness, this you should keep it in mind. So, here area will be your 50 is the length of weld. So, T is the throat thickness, similar weld is there, that is why we multiply 2. So, this total area is 100 T millimeter square. So, what will be this primary shear stress? So, primary shear stress will be equal to your applied load P divided by A, that means here P is 10 kilonewton. So, 10 into 1000 will be the Newton and divided by total cross sectional area is 100 T. So, its unit will be what? This is a shear stress. So, Newton per millimeter square. This we got as 100 divided by T Newton per mm square. So, this is first step of this problem we completed. Second step now. Second step is to find out bending stress, or you can say maximum bending stress, that also you can say. So, bending stress we will find. So, we know bending stress is sigma b equal to m y divided by I, here it will be x x, because that which I have explained in a previous lecture itself. So, here what is m? M is the couple made by force P into the distance between this support to this application of load location. That means, perpendicular distance between this application of load and the support where the welding is done, that you can say. Because here what we used to do, we generally shift that force P to the plane which contain this weld. So, that which I have explained in previous lecture itself. So, I am not going in details about this thing. So, once we shift this load, then what happens, where we are shifting this load, at that location there will be a similar force P and there will be a couple. Here this couple is bending moment. Why this is bending moment? I have already explained this thing in previous lecture. So, here I am not going to discuss again. So, here this M B equal to, you can say this is bending moment. So, here this M B equal to your this load P into eccentric distance E, here you can say, and here y should be the distance between this CG axis, or you can say neutral axis, or you can say centroidal axis of that weld to the farthest weld axis distance. This you should keep it in mind. So, here this y equal to what? Here y equal to, here the farthest weld distance is y1, you can say. So, y1 also is given. So, because this y1 will be 100 by 2, that you can say, that I will just discuss, and Ixx will be here. So, here already we know this MB. So, MB equal to force into eccentric distance. This is force is 10 kilonewton. So, 10 into 1000 into E is 100. So, this will be generally MB equal to, you can say, directly I am putting these things. So, this unit will be your Newton millimeter. Now, here y1 also is known to us, y1 equal to your 100 by 2, that is equal to your 50 millimeter. So, here we have to find out Ixx. So, how to find out this Ixx? So, Ixx means, here I am just showing from this figure itself, you can see So, let this is the x axis and this is the weld. This weld have a length, you can say this is length L equal to 50 millimeter is given and T thickness is also given. So, about its own axis of this weld, let this I am representing x1 axis, okay, x1 axis. So, here we can say that here we will use parallel axis theorem. So, here I am writing by parallel axis theorem. By parallel axis theorem, what do we know? Ixx is equal to our Ix1 x1, you can say that plus area of that weld A into distance from this x1, perpendicular distance between this x1 axis to capital X axis. Capital X axis means where the overall CG is passing, that means overall CG of the weld is passing. This which I am showing here, you can see. Okay. So, this is actually what? This is equal to where y1. So, here this will be area into y1 square. This you should keep it in mind. So, what should be this y1? Y1 will be the perpendicular distance between this CG axis of overall weld to that farthest weld axis distance. Okay, this you should keep it in mind. So, this should be the perpendicular distance. So, here Ix1 means its own axis, about its own axis, the Ix1 will be equal to your, you can say L TQ divided by 12 plus here area will be, area of this weld will be T into L, we can write, and y1 also is given as, directly I am just putting here y1 equal to 100 by 2 whole square. Okay. Now, here one things you should keep it in mind, T is generally very small compared to L. So, as T is much smaller than L or breadth B, so we can neglect TQ terms. TQ terms, here let this is equation number 1, let this is equation number from equation 1, this we can write. So, if we just neglect TQ term of this equation number 1, so what we get? Well, we can get Ixx equal to our T into L into 100 by 2 square, correct. So, what should be the unit of this thing? So, unit should be dimension, means length dimension to the power 4, that means mm to the power 4. So, what should be our sigma b here? So, here the sigma b will be, so here directly I am putting here sigma b will be P into E. So, P into E is directly I am putting all this 10 kilonewton into 1000 is Newton, here E is 100, Y is generally y here is equal to your y1. So, this is equal to 50 and Ixx also I have shown here. So, Ixx equal to our T into L, L is given as 50 and here this 100 by 2 is 50 square. So, this sigma b here we get as this equal to 200 divided by T. What should be the unit of this thing? This is the unit of stress. So, Newton per millimeter square. So, let us consider this equation is equation number 2. Now, we will go for calculating the maximum shear stress. So, third step of this problem is finding out the maximum shear stress. So, this maximum shear stress, what we know, this tau max is equal to, we know that sigma v by 2 whole square plus tau 1 square. So, sigma b and tau 1 is well known to us, because this I have already calculated in previous slide. So, from here by putting this value, so sigma b is 200 divided by t. So, here it will be 200 by 2 t whole square plus tau 1 also I have calculated is equal to your 100 divided by t. So, from here we got tau max is equal to our 141.42 divided by 2 Newton per mm square. So, here we can get that maximum shear stress is a function of throat thickness T. Now, the fourth step here we have to follow, that is to find out size of the weld. So, size of the weld. So, how to find out the size of the weld? To find out the size of the weld, here we know that the permissible shear stress, we know this permissible shear stress tau p equal to how much is given, 70 MPa. 70 MPa means 70 Newton per mm square, because we know 1 MPa equal to 1 Newton per mm square. So, here we will compare that tau p with this maximum shear stress. So, here we will use this condition tau p equal to tau max. By using these things, what we can get? So, tau p equal to 70 and tau max is given as 141.2, which I have already calculated. So, from here we get throat thickness T equal to 2.02 millimeters. So, this one dimension we got. Now, we have to find out what should be the leg length. So, leg length of the weld will be H equal to your T by 0.707. So, this will be generally 2.02 by 0.707, which will be equal to 2.86, or we can say next digit, that is called 3 mm. Because if we consider little bit higher leg length, then our structure will be more safe. That is why here we should not consider less than this 2.86, we can consider little bit higher side. That is why next full digit we consider here. So, this is the different steps we should follow to design a welded joint subjected to bending moment. So, these are the references which I have followed for this lecture, that means for this types of analysis of welded joint. Thank you.